In the interest of time, let's get started. So welcome everyone. Today, we're very excited to have Aaron Held here, who is a DAAD Prime Fellow at Jena University, but also visitor over at Princeton Physics Department, Princeton Gravity Initiative. So Aaron did his PhD at Heidelberg and then had a postdoc at Imperial before his current position. He's an expert in modified theories of gravity and recently has been thinking about how we use observations kind of learn something, constrain gravity. And so today he'll be telling us about black hole astronomy as a probe of fundamental.
Yeah, thanks, George, for the kind introduction. Also, thanks for letting me fill in this spot. I think it's exciting to talk to you, at least for me, because I'm expecting to learn a lot about the astronomy part. And I think that this interaction is really crucial. So I think people from the fundamental physics side and people from the astronomy side definitely need to talk if we need to achieve this. And note that I will view probe mostly as constraints. So the idea that you should have in mind is, are there theories that we can rule out based on the fact that we observe black holes in some way, or objects which look similar enough to black holes in some way? So just George said I did the PhD in Heidelberg, but I did do my PhD actually on high energy physics, on quantum gravity kind of things. I left out the introduction to that for you because I think it will not be super meaningful, but it kind of motivates, if I'm interested in particular theories, what type of theories am I interested in? And you see one of them here. I don't know if you can read it, but it's basically just a correction of the Einstein-Hilbert theory with higher curvature terms. And the first ones that you can write down, they're just Ricci scalar squared and Ricci tensor squared, and then you could go on and build more of these terms. These corrections, they come out of any quantum gravity theory, just because you have loops of gravitons that they generate all these types of higher order terms. So this is like the generic thing that I'm personally most interested in. Then there's a whole bunch of different ways of thinking about theories beyond GR, namely by trying to break the assumptions in a theorem by Lovelock. So Lovelock has a theorem where you can actually rigorously prove that if you list a bunch of assumptions, one of them is no extra degrees of freedom, the other is 4 dimensions, and you want to preserve the symmetries of GR, diffeomorphism symmetry, and you want to have a local action principle. All these assumptions, then the field equations of GR are unique. They follow. There's nothing that you can do. So you need to break one of them, and what people typically break is they break the fact that you have no extra degrees of freedom. So they introduce new degrees of freedom and they make that in a controlled way. So you say, I want GR and I want an additional scalar field or an additional vector field. And then you try to build the most general action of these fields. That's a whole business, and there's a huge community working on that. And in that way, you construct also necessarily theories which do not have ghost. By ghost, I mean an Ostrogradsky ghost. So I mean that the kinetic term comes, that you have two kinetic terms and they come with opposite sign.
When you say no other degrees of freedom, you mean other than gravitons?
Yes. And potentially, I mean, you can always read this as gravity minimally coupled to some intersection. So no other non-minimally coupled degrees of freedom. And in these theories, if you just write down all possible terms, there definitely will be ghost modes. You can think of this as like having an entire function, and you just Taylor expand that function up to some order. You will have terms with plus and minus signs. That holds also for the kinetic part of that theory. So indeed, you will see that this theory has a ghost mode. And there's different ways of thinking about this. One is an effective field theory, that if I would excite that ghost, it's just a truncation artifact. But you can also view that theory as a fundamental theory, and then you can ask it. You should ask, does the theory even make sense if it has a ghost? Or can we exclude it observationally from the fact that?
When you choose which of these assumptions to violate, it's just most natural to choose to allow different degrees of freedom? Or?
To me, it's the mildest variation, but that's, I think, up to a personal opinion. I don't have strict argument for that.
What was the difference between no other degrees of freedom and diffeosymmetry?
You mean because if you
Because
break
diffeosymmetry, I can see
diffeosymmetry,
it as a way to remove degrees of freedom.
you're right that it typically also introduces additional degrees of freedom.
Yes.
But
My question is a bit stupid.
no, I don't think it's stupid, but I think it's a special way of introducing additional degrees. Yeah, so if you look at these types of theories, and if you have ghosts in your theory, there's typically two things that people tell me. One is that you have runaways in your theory, right? If you have a Hamiltonian which is unbounded from below, you expect, even just in simple oscillator systems, you expect runaways. So if you excite that mode, you just expect the kinetic energies to decay into infinite and minus infinite terms. The other is that, and this might be related, that if you have a ghost, then you expect that your initial value problem, really in a PDE sense, your initial value problem is no longer well posed. And I think part of my talk is to convince you that both of these things are not always true. So there actually might be theories where you have sectors with ghosts that are still somewhat healthy. And I'm not going to get much into the physical side, into the runaway side, but there's a very nice paper from 2022 by Cédric Defaillet, Shinjin Kuyama, and Alexander Dickman, where they actually take a simple oscillator model, so no field theory yet, and they can rigorously prove that the motion in their theory is bounded despite there being a ghost. So there are loopholes to these folk theorems, and you will see an explicit counterexample to the ill-posedness in the last part. Okay, with that said, this is sort of the astronomy part. Astronomy is very exciting, and that's why I want to get into black hole physics after the PhD, because I think there will just be a vast amount of additional future data that we can maybe use to probe these. And that contains, of course, the Event Horizon Telescope and VLBI more generally, but also gravitational waves. And I want to structure the talk along sort of what I need to know about my theory to sort of tell you about these experimental things and compare them to what you know from astronomy. And for these type of observations, I need to know the least. I only need to know the stationary solution to the theory, potentially multiple stationary solutions to the theory. And then I can try to probe that as a background geometry for the light propagating in that geometry. And then if you proceed and try to go to dynamics, there's some regimes in the signal, as you know very well, the in-spiral and the ring down, where you can linearize your theory. And again, there might be lots of theories that linearize to the same linearized dynamics, which are only maybe distinguishable in non-linear. And so it's really kind of three different regimes that we try to probe. And I'll try to tell you about at least what I've been doing in all of these three parts. And in the first part, I want to be completely theory independent. So I really want to look at geometries without assuming a particular theory. And then I'll get very specific in two other parts. While other people, I think, also approach this from the perspective of trying to come up with the most general deviations, I then want to be specific and look at this particular. Okay, and I'm going to pause after each part for questions, because I think the nicest way of spending the hour today would be to get lots of questions. Okay, are there questions up to here? Okay, perfect. Then let's start with the stationary solutions part. I have it here in the title that I also call this the Uniqueness Frontier, and I hope it becomes clear why I call it that. And I want to structure that part of the talk along three questions that I get in particular from people outside of the VLBI community about these images and relation to fundamental physics. The first question is, how can we probe fundamental physics if the curvature scales of that object are low? Right? Because what we're looking at is active galactic nuclei, so we're looking at supermassive black holes, and at the surface of that black hole, at the event horizon, curvature scales are roughly of the order of curvature scales here on Earth. So we're probing the same curvature scales, so why would I expect new physics? That's one of the questions that I always get, and I want to address it. The second question that one typically gets, and that's maybe the most interesting one for us today, is how can we tell apart which part of that image is influenced by astrophysics and which structures of that or future images might not be influenced by astrophysics and can still tell us about the geometry, even if we make no or very little assumptions about the astrophysics. And then if I get to it, I want to spend the last part about talking about what if there were no horizon. Okay, so let me start with this question of curvature scales. So I already told that curvature scales are indeed low, but still that's not the only scale that new physics can enter with, right? So I've made a little plot here, and you see indeed on the y-axis, you see curvature scales. Everything is given in Planck units, so that's why you have tiny numbers here. But if you would pick different units, that wouldn't change the overall picture. So you have curvature scales on the y-axis. On the x-axis, since I'm looking at stationary solutions, I'm plotting the integrated mass at infinity of that solution. And so it's the mass of the source, right? So that's another sort of parameter of your stationary solution. And indeed, you can see that I've listed I put in this plot different objects. And up here are the binary systems, solar mass binary systems that LIGO sees, this line. And then there's a neutron star system that LIGO saw. And then here there's the horizon. So anything past in that gray area is behind the horizon. And then there are supermassive black holes, which we have observed, and they are at lower curvatures. But also people probe. So we have very good data, of course, on Earth scales and sun scales. People also probe, for instance, at the same curvature scales, very tiny objects, and they ask, is gravity behaving on that scale? If the source mass is very tiny, is it behaving in the same way? And that's definitely a meaningful test, right? Because we could have physics which is tied to the source mass and not to the curvature scale. And that also applies to the supermassive black hole object. So what one needs to justify in the end, and we don't actually have many good theoretical examples of that, is to find theories where you can have multiple different black hole solutions, some of which behave like this, and some of which behave like this, and then you want to form an argument, maybe a different accretion process, or maybe even physics entering at a large curvature scale, a low curvature scale, that these objects are different. And I can't do that today. I can't give you such an example, but I think it's a possibility worth probing.
You also could put angular momentum on here.
Yes, I could do exactly the same plot with a source mass. I could do with the.
I mean, is this? I guess if you don't have a theory that has this mass, you don't necessarily have one referring. But again, just in terms of naturalness, it's more natural to think that would be dependent on masses.
No, I don't think so. And in fact, what I think, that's why I would call that section uniqueness, probing uniqueness, because what we're doing here is we're probing uniqueness theorems about black holes or about the asymptotics in vacuum of GR. And there's a couple of them actually in GR. The obvious one is that Kerr black holes are unique. The other obvious one is that in spherically symmetric spacetimes, we have Birkhoff's theorem. So we know that if you have any source which is spherically symmetric, the outside must be Schwarzschild. That with spin you have less control over that, even in GR. So you don't know that the outside is Kerr, but you know that the leading order asymptotics of the outside must still be Kerr. And so that's what you know from GR. And you can ask, if that's true here, is it also true here? And that's a meaningful test of uniqueness theorems in GR and a meaningful test of GR. And that's sort of how I would approach testing, using these images to test the underlying field. And then we want to do that, but we want to do that in a way, of course, that is, if possible, fully general. So we want to make the least assumptions about what modifications of the uniqueness theorems I can expect. And so here I've sketched the whole class of stationary axisymmetric and asymptotically flat spacetimes. And somewhere in there is curve spacetime. But curve spacetime is also special in a bunch of other ways, which sometimes are used to construct these general classes. So one is that curve spacetime is what people call circular. And this is not in a simple, meant in a simple geometric sense. That's actually a mathematical property. And you can think of it as inverting the rotation sense of your spacetime related to the Boyle-Lindquist angle phi, and inverting the time direction in your spacetime. And if you do both of these transformations at once, if your spacetime is invariant under those transformations, you would call it circular. You can also tie it to properties, formal mathematical properties about the Ricci tensor. And that's why in vacuum GR, so if the Ricci tensor vanishes, it's trivially fulfilled. Okay. And then you can go even further, and there's another subclass in which the spacetimes are integrable. So you have a hidden constant of motion, which is very useful mathematically, right? Because then you have single integrals which you can at least express. But again, this need not be true for all the spacetimes that we want to look at. And so if I want to construct the most general class of these integrable theories, well, here's what it looks like. People know this since the 80s. It's constructed, you can construct the general metric, and it has 6 free functions. They are all free functions of only a single coordinate. So you can think of the x1 being the radial coordinate and the x2 being the theta coordinate. So it's the non-killing coordinates. And these functions only depend on one of them. That's what makes this sort of the most restrictive class. As I said, it has a hidden constant of motion, and you can integrate your geodesics, and it turns out to be a subclass of this larger circuit.
Are these vacuum solutions?
Sorry?
Are these vacuum solutions?
2GR?
Yeah.
No, they're
The general, or do you need a source?
This is not an additional assumption here. So this makes no assumption about even, I think, the asymptotics. So you need to, in addition, now put the asymptotics, which gives you some constraints on these functions. And then you might want to do an expansion of these functions either around asymptotic infinity or around the horizon. That's what people typically do. And other than that, so the class of spacetimes is no longer Ricci flat. So it's not a vacuum solution. Okay, so if you make the class larger and you go to circular spacetimes, now you can think of the metric being block diagonal. So you still have the structure that you can form 2 different blocks, one being the killing coordinates t and phi, and one being the non-killing coordinates. But you no longer have this special form, so all of these can now depend on both of the non-killing coordinates. And you can use your coordinate freedom as much as you can, and you can see Lewis and Papapetrou so that you can cook that down to 4 free functions of 2 variables. That's the best you can do. And that's again a class that people. And you can go even more general. You can also allow for breaking this circularity. And there we do have counterexamples. So we do have both in GR, we have neutron star solutions, which are non-circular. And outside of GR, we have even black holes in scalar tensor theories, which are also non-circular. So that we even have examples of potentially interesting physics in that larger class. And then, of course, it becomes even more difficult. And to my knowledge, there's no clear understanding of whether you need 6 free functions or more. All right, I'm not going to bore you with this. This is something that I'm super interested in. But for us today, this just means that we will make a metric ansatz. And then we will expand each of the functions in this metric ansatz either around the horizon or around asymptotic infinity. In fact, here it's an expansion in somewhat both. Some part of the expansion is around asymptotic infinity, and part of the expansion is around the horizon. Not even a Taylor expansion, but a continued fraction expansion. The interesting thing about that is that then you can put Kerr in that expansion, and it's exact. So you have to go up to a certain order, but then Kerr spacetime is exactly represented. I think that's a positive thing.
Wait, so what does that mean?
Sorry?
When you have an expansion, I didn't understand that.
Well, you set up a particular way of expanding these functions.
Mhm.
And that guarantees you that if you expand up to a certain order, since you write down continued fractions. So some parts of the expansion, they go like, so you define coordinate x, which is something like this. And then in that x coordinate, your expansion will look like, and so on. So as one of these then vanishes, all of the other ones don't matter anymore. And that allows you to find a way of constructing that expansion such that if you pick the coefficients of that expansion in this particular way, you have exactly Kerr space. That's all. And you don't need to worry about this table too much. I'm not going to go through all of the coefficients. What this is supposed to tell you is that there's a huge parameter space. And that's something that is kind of obvious. If you want to cover all deviations from GR, it's going to be a big parameter space. And we also expect some degeneracy with respect to what modifications you can put to that shadow, right? Because we're only observing like an effective part. We maybe can't learn everything. Yeah.
I may be misremembering something, but numerical PR folks say there's no uniqueness theorem for Kerr. So what is Robinson's theorem lacking? If that's true.
There's no, you can't guarantee stability for Kerr. Is that what you're saying?
No, I mean, they say there's no Birkhoff's theorem for Kerr, but Robinson's.
I think Robinson is just a statement about Kerr being the only black hole solution, right? And what you're asking is the extension of Birkhoff theorem, right? Which tells us that even if you have no black hole outside of the compact object, so if you have the vacuum outside, looks like Schwarzschild. So in Kerr, we don't have that. That's true. So the outside need not look like Kerr. We only have the asymptotic statement that the first leading asymptotics must match that of Kerr. That's my understanding. Okay, so getting back to this, we do expect a large parameter space and degeneracy. And so we better need tools that are somewhat efficient, right? Because if we want to probe that, we need some degree of efficiency. And that we will pick back up in the second question. So now we have this class of geometries. How can we separate it from astrophysics? And there have been some approaches to that. The first one, which you're probably not even able to see, this really takes a single theory beyond GR and tries to perform full GRMHD with that theory, and then compare that to the GR. Well, there's, as you know much better, there's also there's also assumptions in GRMHD about the astrophysics. But apart from that, even if we were able to simulate that perfectly, it's just a huge computational effort for a single theory. So if we were to do this with all these spacetimes, it's presumably not feasible. And that's why people want to find some way of calibrating or finding these deviations in a more general way. So there's a paper here by Junzi, Sartis, and Özil, where they do exactly that. They take a large class of spacetimes and a large class of disk models, and then they just perform all of that, and they try to find the mean deviation that you get from a theoretical quantity, which you can find on every geometry, which is the critical curve, and to the shape of that donut that we see. I don't properly understand that. For me, it's a black box, and that's part of why Alejandro and we wanted to get more into this business and find a different approach. And then there's also another study in the same direction. All right, so if we want to do that, we need to understand a bit better, and I just want to make sure that everyone is on board, what we are actually observing. We're observing light around, and this is a nice simulation by Michael Johnson. George was also involved. What you will see the black hole here, and here's the screen of the observer. And the simulation is performed in such a way that the equatorial plane of the black hole is roughly aligned with the screen, what people call face on. And then you can count in the geometry how often you can throw light rays which cross the equatorial plane once before they arrive at the screen. And these are all of them, and you can imagine they can arrive in basically anywhere in the screen, right? Because they can go very far out, cross the equatorial plane once, and arrive at the screen. That changes if you cross the equatorial plane twice. So if you cross twice, here are all these rays, a bunch of them. They actually all come in a very small region of the screen. And then you can go on and you can do that for 2 times, 3 times, 4 times. Actually, as you do that infinitely many times, you converge to that theoretical quantity that I was mentioning, maybe the critical curve or the boundary of the shadow, which is really the boundary that distinguishes points on the screen, which can have come from asymptotic infinity, to points inside, which can have come from the horizon, which if you ray trace backwards, they have fallen into the horizon.
So maybe the point, what we're seeing right now, is there anything else other than the black hole and the photos that are being shoot?
Yeah, so what you see in the image is really an emission model. And you can integrate the emission along the rays.
Okay.
So yeah. What I want to say is that if there is an experimental way of telling apart these different emission classes, so if there would be an experiment that separates the lensed emission from the direct emission, then maybe we can use that. That's a big question mark, and I think we should discuss that. Whether that's possible. My personal opinion is that currently it's not possible, but maybe it's possible even with Earth-based observations. And if people come up with a reason, then we can go and compare it to the geometry. And I want to be involved for now only in that latter part. So I will assume that people hand me from experiment the statement, here's a region in my image, and I'm confident that this is the region. I'm confident to some degree that this is the region where we have received lensed emission. Maybe we can also do something in terms of time dependence. We see like a hotspot moving, we see it twice. Maybe that's suggested that the second time might have been. All right, so I will just assume that. And then I'll be interested in finding a fast way to do that on these classes. Okay, and for that, lensing bands are useful, which really is now the theoretical region in which you can have achieved a geometric region in which you can have achieved emission, which is at least lensed once, so which has at least traversed the equatorial plane twice. So this was the second run that you saw in this first video. And then you can put that region, and this is an example here in Kerr spacetime changing the inclination. And you can see that the region deforms with inclination. And just as well, it deforms with all the other parameters in your spacetime. All right.
So the emission model here was what?
So here there was an emission model.
Yeah.
Here there's no emission model. This is a geometric statement, right? So this really just means that out here, I've gone through the equatorial plane once. In here, I've gone through the equatorial plane twice. And so now this statement becomes relevant if you assume that the emission has come from close to the equatorial plane, right? That's somewhat an assumption in what I'll be doing. Okay, and now you can go and I've developed a code that does that not just in Kerr, but does it to any geometry and finds that boundary. And it just goes around. And you can then, if you can do that, you can find these regions, which are the gray bands here, in a beyond GR geometry. And you can ask, does that feature that people have separated, does it fit into the geometric region? And if it does fit, there might be some emission model, maybe it's a weird emission model, but there might be an emission model which does that. So I can't exclude that geometry. But the other case, where I can't fit that experimental region in the lensing band, that really means there's no equatorial emission model which can have generated that emission that I see. So then I'm really starting to disfavor these geometries.
That would be used for the rest of scene. When you say equatorial, you mean no thickness whatsoever.
Yeah, you're right. Strictly, this is just true for a razor thin equatorial disk.
Okay, my question is, if you were to increase that slightly, what is the impact on this?
Yeah, I have a backup slide on that. If you're interested, we can talk more about it. So basically, this band will widen a little bit. So the band will widen with increasing, for instance, the angle of emission that you have. It will shrink in width if you pull out emission, if you don't allow emission at radius infinity, but you pull that in. So you could make assumptions like, I want to have emission up to radius 100 m, and I want to allow for emission at some angle, and then you could rerun these. And that will give you, that will somehow change the astrophysics assumption.
Yeah. So my understanding of this is that you have some theory that you can represent coefficients, and so for that set of coefficients, you find the gray region. It corresponds to these coefficients, and then you ask, okay, does the observation lie within the gray region? So suppose that I take the EHT observations. They're incredibly blurry, but still there is some range to it. If we assume that the n equals 1 or n equals 2, whatever, has to lie somewhere within that very blurry ring shape, does that provide any constraints?
Yeah, I mean, you're basically asking if you would run the same thing with a large.
Yeah.
Yeah, I think the reason why I'm not in favor of that is because that excludes more cases. And you can understand that in terms of, you really want to fit the full thing that you see, at least in this way, it would exclude more cases. You want to fit the full thing where you have confidence in the experiment. You want to fit it in the lensing band.
But if you just look for intersection between the two sets, you have some.
You just maximize the intersection and compare that to GR. Yeah, that you could, for sure.
Is it interesting if you done?
I haven't done that yet. So actually, this still is a big task to do. Similar task like George is proposing are big tasks because you have a wide parameter space.
If I may, if you do see this EHT big tunnel, it's mostly from the direct image.
Sure.
So what happens is like basically you won't be able to put a meaningful constraint because it's from in your observer, you have the upper location of the event horizon up to infinity. So everything is more or less. So even if you go to the slide that Aaron was showing, here basically if you were able in that, let's say the one that has the tick, you have the upper location of the horizon and then everything else is direct emission. So it will be very hard. However, here you just have the lens one, as Aaron was saying, and then that you can do. So even for, there is a test actually for going to the next photon ring, n equal to, as you know, in your paper with but that one is really independent of the astrophysics. So you need to actually this one is an open question if it's actually giving really powerful constraints. So we can constrain some of those for now. So from the direct image, you will just see basically no constraints.
I guess another way of saying, how big can you make the gray region with reasonable coefficients?
Well, I wouldn't want to judge the coefficients as reasonable. You can make the gray regions very big. In particular, you can, if you change things close to the horizon, you can deform the inside very far. And outside, if you change the asymptotic. Yeah, I mean, show some examples. I will focus on the asymptotic parts. So on the mass, on changing mass and spin in the space-time. Note that I can now change the mass and spin in a different way than in curve. So I can change the mass, and I can change, in particular, the spin to even values larger than the curve maximum value, because I can still maintain a horizon. This is what the mass does. You see, it's not just a rescaling of the image, because I'm changing only the asymptotic mass. And yeah, this is what happens. In that case, it makes the ring thinner. If you go in the opposite parameter direction, it makes the lensing band wider. And then you can use deformations, and that's, you might have these shifts in mind from the spin. That's actually what this parameter does. It changes the spin, but then it can deform further than the spin back. And then this is exactly the case that you've seen before, which I would say, if we have a confident detection of this being fairly circular, then we can confidently exclude that. And then we can make a statement if we assume emission close to from the equatorial plane. And now I'm currently working with Alejandro to run larger MCVCs on this set of parameters.
Just to understand, in principle, since we're not aligned the right way and just would have some sort of inclined this, you could do the same that you're doing with something like that.
Yes. Yeah.
How would this change?
Yeah, as I said, if you allow for emission away from the equator.
No, that's not what I meant. If you have
I didn't really mean an inclined disk with respect to.
Because there is no reason for us to assume that that this completely edge on, right?
Mm-hmm. In principle, yes, but I would have to change significant things in the code, because now you're defining a plane with which I'm supposed to count, which it has no correlation with the unique symmetry plane of the space-time, right? But since I'm doing things numerically, I think in principle there's no abstraction. But so then, what angle would you pick?
Well, maybe George knows if there is some constraints on this from observation.
But isn't it a reasonable assumption that the close to the black hole emission, if it's an accreting process, is aligned with the spin of the black hole, or it's perpendicular to the spin of the black hole?
Basically, yes, but it's a priori. But are there no constraints on this from EHT?
I've seen,
From the EHT, certainly not.
yeah,
No. Okay.
and in simulations, I've seen many. Actually, there are ways like that this might break multiple times. Like you don't just have one inclination.
So there's one more thing that you can, if you want to be even more conservative and you don't want to put that plane, I think there's a way of defining sort of a global lensing band. Essentially, it pulls you down one order. So surely the lensed emission, which goes around 3 times, it must lie in the n=1, independently of wherever it comes from. So then I think we definitely need space-based observations to do these constraints, but then they are completely independent of any astrophysics. All right. Yeah, I think I'm actually going to skip that part in favor of time, in favor of getting to a little dynamics. So first, the linear dynamics of that theory that I looked at in the beginning. And I want to focus on the ring down part, just because that's related to stability. So if you have a single black hole and you try to understand its quasi-normal mode perturbations or its linear perturbations, then you're analyzing when is that black hole stable. In particular, if you find modes which are unstable and sufficiently fast unstable, then you expect that these objects are not even stable in the theory. So now you have trouble explaining explanations with such compact objects because they would just decay. And that's a way of excluding additional fields, because many additional fields introduce these type of instabilities. Notice that there's now not just linear dynamics, there's also the background which matters and the boundary conditions. So there's 3 things that you actually assume in that process. And also if you're probing quasi-normal modes in that end of your gravitational wave signal, you're actually probing a combination of these 3 things. All right, the example theory that we're looking at is that quadratic gravity theory. And this is sort of the result that I want to explain to you. Where you see now the theory has multiple black hole branches. So these are the lines here. And I'm plotting the horizon radius and the asymptotic mass m. And of course, for Schwarzschild, we know that they are related by g equals 2m or 2gm, so it's just a straight line. So this is the Schwarzschild solution. And indeed, since the theory couples only the Ricci tensor, it makes sense immediately that any solution to vacuum GR is still a solution to that theory. In particular, holds also for Schwarzschild. And then there's a different branch of solutions, which is harder to get, which you actually have to, even the background is not known analytically. That's why it's actually points that I'm plotting here. But there's a second branch, and you can ask which of these branches is stable given some parameters and which are unstable. And that's exactly what we want to do. And we will see that large black holes in both branches, so these green parts, right, large in the sense of horizon size, they will be stable, and small black holes will be unstable, where large and small is distinguished with respect to the fundamental parameters in your library.
So the idea is that since it were possible for these things to be unstable, which you mentioned they would decay.
Yeah.
In the form of what? Would that be observed by LIGO, for example?
That's not, so in the form of what is not known. So because we only do the linear part here, we can only say there's an onset of the instability. To actually know where that goes is exactly why I'm interested in doing like nonlinear simulations in that theory. In particular, if you have an onset, you would want to see where that goes.
But would it go somewhere else other than gravitational waves?
Yes, it can. I mean, for sure there will be some excitation that makes it out to asymptotic infinity, I would guess. But it can even be that the whole that you excite that runaway in that theory, right? So that you either break the EFT or that you really make the vacuum decay to something completely different. That you even propagate something else out to asymptotic infinity beyond just gravitational waves.
I'm just trying to understand. So when we hear that LIGO has, observed the measure of two, 37 mass black holes,
yes.
What convincing evidence we have that actually that went to some other black hole as opposed to, this sort of thing happening?
Yeah, I think this is what we eventually want to get at with these type of theories. You want to find theories which have a different branch of black holes, which are stable. And then you want to simulate them and you want to try to constrain the changes in the gravitational waves. So I'm not sure if I'm understanding or
I'm just trying to understand whether we have any way to understand this with observations from LIGO.
Not yet, and for sure not just from the linear analysis.
So is there an analog, the area theorem in these theories, or does all of that completely break?
Yeah, I don't, certainly not an improvement. Okay. And I mean, indeed, if the black hole will decay from here to here, its area will increase. All right. Now, just to give you a little flavor of how that works, you actually do linear dynamics. So you take this theory, you linearize it, you see its degrees of freedom, you see the massless graviton, you see an additional massive scalar, which is related to the R squared term, so the Ricci scalar squared term, and you see a massive spin 2 degree of freedom, which has the opposite kinetic term, which comes from Weil squared or Ricci squared. So this is the ghost.
Why there's no spin 1? This additional also. Reason why there's no additional massive spin 1? I don't know.
I'm not sure, like when you're asking me, is there a reason? I don't have a very deep explanation of that. For me, it's just, I expand these in a linear way.
In case it's a massive spin. Okay. No, maybe I can answer that.
So I can still couple that theory minimally to matter. So I can still have a massless spin 1 if I want to. Okay. Then I decompose that in the usual spherical harmonics. I focus on axisymmetric perturbations, and I focus on monopoles. The reason why I do that is because I want to find long wavelength instabilities, because these are the ones that I expected. And then you can write down this equation where I was saying this comes about from dynamics and from background. People call these master equations. And you can try to solve these equations for the modes that you can excite. And then these modes come with e to the minus I omega t. So whenever you find a positive imaginary part, that's actually an instability. Of course, you need to set boundary conditions. And if you find a positive imaginary part, it's an instability. And if you find a negative imaginary part, it's a stable. Okay, and that's exactly what you can do, both on the Schwarzschild background. This is a result that's been known for quite some time. And I'm calling this a Gregory-Laflamme instability, which you might know from 5-dimensional, higher dimensional physics, because the master equation is exactly the same, which tells you that the linear dynamics for very different nonlinear problems can actually be the same.
Is the second order equation on the field, is that's what we call the master equation?
Yeah. This one?
Okay.
Yes. That's the equation for the monopole mode in that theory. Okay, and you see it has a region in which it has a positive imaginary part, so where we expect an instability. And that tells us that this part here is unstable. And then you can do the same thing on the other background, and that's what we recently were able to do. And you find the same picture, that there's an instability for the small parts. So then we now kind of have an understanding of these two black hole branches in the linear regime. And now we want to go to the nonlinear theory from that. Let's skip that part. And so again, we want to look at that theory, and we want to somehow achieve a nonlinear dynamics. So in the end, where we want to go is really binary systems. And this is a benchmark test that we're currently running. We are now on the way to do 3+1 simulations. So for that, we need a well-posed initial value problem, right? Because even if you don't care about the fundamental thing of having well-posed evolution for all time, it's a globally well-posed initial value problem, you need to worry about this if you want to perform numerical simulations. Because if you don't, then as you increase your resolution size, your simulation time goes down. So then you can't really perform simulation. So in GR, of course, that's known, that we can have that. And even in quadratic gravity, it's also known there exists a formal proof of local well-posed existence by David Noakes from 83. This is what got us excited in this theory. And now with Hyun Lim, our collaborator, I'm trying to do simulations both. We've done that in spherical symmetry, and we're currently doing that in full 3+1. So that's again the theory. Now phrased in terms of second order equations. So right, I can take the equations of motion. The equations of motion, the original ones are fourth order. But I can introduce fiducial degrees of freedom, and I can cook them down to a second order set of equations. And you can actually see now that these again correspond to the massive spin 0 degree of freedom and the massive spin 2 degree of freedom. So you can find the linear degrees of freedom in that nonlinear set of equations. Yeah, thanks. And then you can reduce further to first order variables, which is key in the proof by David Noakes, because you can then take additional derivatives and you can diagonalize the system, or you can at least quasi-diagonalize the system, which means you diagonalize the part with highest derivative. And that allows you to apply fundamental theorems, the same actually ones that you've applied in GR, or that Yvonne Choquet-Bouha has applied in GR, and you can thereby establish that there must exist a well-posed initial value. And now what we want to do is we want to like explicitly formulate that initial value problem and put it on. And yeah, I'm not going to take you through the whole spherically symmetric procedure in favor of time. This is actually now a simulation, and what you see is a convergence test of that simulation. So you see the Hamiltonian constraint in that theory, as a function of the evolution time. And you see that the constraint violations decay in a nice way. And if I change the initial amplitude of my noise, so I can impose like numerical noise at a certain amplitude, and I can see that that is a controlled way of in which this noise behaves. In particular, if there was an ill-posed sector that I excite, then I would expect at some point that there's constraint violations in finite, they diverge in finite time, and the simulation crashes. We find no evidence for that. And that's about flat space-time, that's about Schwarzschild space-time. So we can actually now go and we understand that even the nonlinear theory we have under numerical control.
Why do you pick these masses?
Why do I pick these masses? So these masses are interesting because this is in the regime where I would expect an instability. So where I would expect to excite the beyond GR sector. Note that I haven't, does not tell me anything about physical stability. It just tells me about numerical stability. And we're now in the 3+1, we're currently struggling to understand the physical stability. But yeah, that's the regime where we would expect some instability.
But your coefficients scale inversely with M1 and M2, right? So these would be large coefficients.
Yes, the smaller you make the masses, the larger you make the coefficients in Lagrangian, and the smaller you make the masses, the more sure you are that you have an instability.
Right. So this would be in the EFT, this would be more than 100 coefficients, right?
Yes, although these are dimensionless quantities in the EFT, so really I would say that the weird coefficient is the Newton coupling, because that is a dimension full. So it's similar to the cosmological constant problem. You would then have a hierarchy problem between these dimension-less coefficients and the Newton coupling. Actually, one reason why I'm interested in these theories is to try to understand in how well they can mimic gravity, they can mimic GR. Because if they have a vacuum sector that mimics GR very well, they have high energy properties, quantum gravity properties, which are much nicer than GR because they have different propagators. That changes the question of whether I can quantize these theories in a QFT set. So if they mimic GR very well, I'm very happy. And then doing the whole story again in 3+1 dimensions, you can start from Noakes's proof again, and you can try to do a decomposition in just a usual ADM decomposition. And then you can identify again the degrees of freedom, the metric, the scalar degree of freedom. And now I've reshuffled the massive spin 2 in these variables, and you can formulate a huge set of equations, which looks very ugly and was very painful to derive. And you can try to perform just as in GR. You perform, for instance, BSSN splits, and then you perform the same simulations as in GR. And again, we can now do convergence tests. It all looks fine. And this is very preliminary. The next slide, so please don't be angry if it changes in the final paper. So we can actually now simulate these theories through merging. What we see is that even if there is the instability, and we're currently searching for the time scale, maybe we have to tune these to like make the instability be sufficiently fast. Currently, we see that there's basically no deviation, which means that there might be in these theories a sector, which makes sense again, like we had Schwarzschild being a solution of the theory, maybe also the full solution of GR, which is a dynamical nonlinear solution here, right? Because it's merging black holes. Maybe it's still a stable sector of that field. And I think that's what we're going to be after.
Oh, Psi4 looks the same.
Sorry?
Psi4, yeah, the graph tissue.
Well, if really we haven't checked it explicitly, but I very much expect that if everything up to numerical noise is the same, then in GR also Psi4. And from like a theoretical perspective, this makes a lot of sense because any vacuum solution to GR, and this is a vacuum solution to GR, is also a solution to that field. The question is if that solution is stable, or if I have the whole nonlinear dynamics, maybe I'm exciting the runaway. So the question really is not, is there a sector which is GR, vacuum species GR, but is there a stable sector which is vacuum species GR?
I think naively, if you keep decreasing these masses, you would have like more stringent tests. Like your coefficients would start
Yes,
going up.
yes.
So why these particular values? Like you can go lower and test it more stringently.
So there's actually a threshold value where, so if I go back to, maybe this is nice because it just leads into lots of discussion presently. If I go back to this, this slide, you can try to find for a given black hole mass or for a given horizon radius of the black hole, you want to find your M2 for which you're somewhere in the regime where you, of course, you want to be in the regime where you have an instability, and you want to be in the regime where the instability is fast. Right? And I think that's something that we didn't do in these simulations. The one that you see is mass being 0.01 and black hole masses are just set, are normalized to 1 in that theory. So then you would be somewhere here. So then you would have a time scale here. And I can now, in hindsight, I can say that the time scale of that instability, where I would expect the perturbations to grow by 1 order of magnitude, is outside of what we've simulated. So what we want to do next is we want to fit the peak of those simulations and see that we can recover this lineage. But then I still think that the simulations are already exciting because they tell us that if you're in this regime, where the linear instability grows very, very slowly, then the whole nonlinear dynamics doesn't introduce any additional instabilities. That's, I think, what we like. Okay, I guess I'm basically done. I just had that as an outlook on what's to do next, but that already leads me to what to do next. So I guess, thank you.
I think maybe time for 1 or 2 questions.
So it's how many effects don't play much of a role if the linear growth rate is tiny? Isn't that one would naively expect?
If there's no additional, it's the same question as if you have, or I think it's a similar question, if you establish the stability of the Kerr solution linearly, then yes, you have established that small perturbations go back. And you're asking if that not establishes whether Kerr is nonlinear. And I think you can, in principle, you might have sectors in the nonlinear theory, which in particular you have the ghost mode, right? So you might have, actually many people have told me don't even go and simulate that theory, it has a ghost, it will look ugly. So I'm kind of happy if the theory can just reproduce GR.
Sure.
To me, it's an important statement.
Any other questions right now? If not, we are going to lunch and then we're having a dinner this evening. I think there's like 1 or 2 spots left for the dinner, so if you're interested in that, please sign up. Other questions? Otherwise, we go to lunch. Great. If not, let's sit down.